Yes, good afternoon to all the participants and good afternoon to Dr. PM Aneesh. Good afternoon, sir.
Good afternoon.
Okay, so sir, shall we start?
Yes, sir. Yes, sir. We can start now.
Okay, so a very good afternoon to one and all. We are about to begin the afternoon session of the faculty development program, Photonics and Laser. So in the afternoon session, we have a very special guest, Dr. PM Aneesh. He's a professor at the Central University of Kerala. And Dr. P.M. Aneesh has took his PhD from the Cochin University of Science and Technology. After that, he has done his postdoctoral research in ENEA at Italy and also at Indian Institute of Science, Education and Research, Trivandrum. His research interests include optoelectronics, organic electronics, and transparent electronics, and he has made a lot of international journals of high repute, more than 20 journals to his credit. So, on behalf of MES College of Engineering, I would like to welcome Dr. P.M. Aneesh to this faculty development program. So, sir, please.
So, good afternoon. Am I audible to you?
Yes, you are audible, sir.
Okay, thank you. So, thank you, Mr. John, for the nice introduction. And first of all, I would like to thank the organizers, especially Dr. Sunish, for inviting me to this 5-day FDP program. He has also mentioned that the yours is a mixed group, that is, participants are from have different backgrounds. And he has also mentioned that the students, some MSc students are also attending this program. So for the benefit of all, I'm just have taken a general topic, that is semiconductors, PN junction and LEDs. And at the end, if the time permits, I will show you some of the research work that my group has carried out for the past 8 years. Okay, so moving on to the topic, let me share my presentation. Okay. So I'm starting with the basic concept of semiconductors. So the semiconductors, you all know that semiconductors are the material can be classified in terms of the conductivity. That means the material, in terms of the conductivities, material can be classified as metal, insulators, and semiconductors. So in which the conductivity normally we represent in terms of, these are the parameters, the values of the conductivities. The metal, the conductivity is in the order of 10 raised to 4 to 10 raised to 7 Siemens per centimeter. Whereas the insulator, the conductivity is in the order of 10 raised to minus 12 to minus 18 Siemens per centimeter. So, but the conductivity of the semiconductors lies in between this metal and insulator, that is 10 raised to minus 6 to 10 raised to 3 Siemens per centimeter. Now, how one can change this conductivity of the semiconductor, that is a topic. So there are different techniques. So the conductivity can be changed by the first technique you all know, that is the basic concept, that is called the doping. So doping means when you add the intrinsic semiconductor with some pentavalent impurity or trivalent impurity, you are making that as a p-type semiconductor or n-type semiconductor. So in that way, you are actually changing the conductivity of the semiconductor. So another way is that, so normally you can say that the semiconductor have a valence band and conduction band. So they have a separation that we call it as band gap. So when you increase the temperature or when you heated the semiconductor at a high temperature, the conducticity can be changed. So that means you are allowing the electrons to jump from valence band to conduction band. So in that way, you can change the conductivity. So the third technique normally is the illumination light. So when you shine the semiconductor with some sort of light of particular energy, you can increase the conductivity. So these are the semiconductors. So the conductivity is in between that of insulator and semiconductor metal. Okay. Now coming to the different properties of the semiconductors. So normally when we will discuss about band diagram. So let us consider, before that, let us consider a single hydrogen atom system. Okay, single hydrogen atom means you can see there is one electron system, that is one electron is revolving around the nucleus. So the potential, we can calculate the potential is given by minus 1 by 4 pi epsilon 0 q square by r. There is a potential. So when you put this potential in your Schrodinger equation, you have the Schrodinger equation. So when you put this this potential in your Schrodinger equation, and if you calculate the energy eigenvalues, you can see the energy eigenvalues are given by minus 13.6 divided by n square. So there is a constant term divided by n square, where n is the principal quantum number. That means when you change where n is equal to 1, 2, 3, etc. So when you change the n equal to 1, there is a particular energy level. When n equal to 2, there is a particular energy level. N is equal to 3, like that. So these are the energy levels. So this is for a particular single hydrogen atom systems. So, but now let us consider two hydrogen atom systems. So suppose these are the two hydrogen atom system. Suppose these two hydrogen atoms are very far apart. So that means electron in this one hydrogen atom does not experience any electrostatic interaction of this electron in the other hydrogen atom. They are very far apart. So that is similar to that of single two hydrogen atom system. So they have this discrete energy level itself. But when you make, or when you when the distance between the two hydrogen atom, if it is very less, or the electron in the one hydrogen atom starts seeing the electron in the other hydrogen atom. So there is a interaction between these electrons. So as a result of, there is a Pauli's exclusion principle. The Pauli's exclusion principle says that no two electrons have all the same four quantum numbers. So these two electrons cannot occupy in the same energy level. So that means the energy level, whatever the energy level, suppose n equal to 1, that has to split into two energy level in order to accommodate these two electrons. Okay. So this is for the two electron systems, okay, two hydrogen atom system. But crystals, that are a collection of atoms. So that means that they contain millions of atoms. So each atoms, in order, if you want to accommodate all these electrons, this level will split into n number of energy levels. So as a result, each energy level will split into number of energy levels, and that is this one. So that means n equal to 1, there will be a large number of energy splitting, and the separation between the energy levels will be very, very small. Okay. Similarly, n equal to 2, there will be a splitting. N equal to 3, there will be a splitting. N equal to 4, and etc. So there will be a splitting of the energy level, you can see. But normally you can see electrons are available, or the free electrons are available in the valence band and the conduction band. So only you can see the electrons are in the bottom two levels. So that means the bottom level we call it as valence band, and the next higher energy level we call it as conduction band. So these are the concepts. So this is actually a valence band and conduction band concept. So, and which are separated by a distance which is called a band gap. So the valence band and conduction band which are separated by a distance, we call it as band gap. So depending upon the band gap, material can be classified into the metal, insulators, and semiconductors. So in the metal, there is a conductor. That means that normally we can consider as a overlap bands. There is a valence band and conduction band, that we have an overlap bands. So electron you can see in the conduction band as well, and in the conduction band you can see a large number of vacant space. So electron can move from one point to another when you apply some electric field. That is why you can see in the high conductivity in the case of conductors. But in semiconductor, there is a separation. The separation is normally in the order of 0.1 to 3 electron volt. The separation between valence band and conduction band, there is the band gap is in the order of maximum up to 3 electron volt. So if the separation is very large, so then if it is greater than 3 electron volt, normally we call it as insulators. So even when you give even at a high energy, when you give high energy, electron cannot jump into the conduction band. So that means that are and that is why it's called insulators. Okay. So this type of structure, that is band diagram, will give you only this idea. Okay, only this valence band, conduction band, and the separation. What is the band gap? Such things. But if you want to study more about the semiconductors or more about optical and electrical property, you need to consider the band structure as well. Okay, so that is why we have several type of theory like block theorem, etc. So the block theorem says that, for example, let us consider periodic atoms. So crystals are similar, just like you can see, crystals can be considered the periodic arrangement of atoms. So each atom, if you consider the potential is varying like this one. When in the right side, you can see that the potential energy variation is like this. Okay, so the potential is varying like a periodic way. So the block, the motion of the electron in this crystal is governed by the laws of quantum mechanics. So if it is a single hydrogen atom system or a single atom system, it's very easy to solve the Schrödinger equation. But if there are more number of atoms, or if there are a large number of atoms, it's very difficult to solve the Schrödinger equation. So that is when the Bloch suggested, or Bloch observed, that we can see that the potential is varying periodically. So Bloch suggested that if potential is varying periodically, the probability of finding electron should also vary periodically. Okay. So the probability means if you have in the quantum mechanics, you might have heard about the wave function concept. So wave function, if there is a wave function psi, the probability is given by psi square. So the probability is, but if since the potential is vary periodically, the probability of finding electron should also vary periodically. So that it means the wave function is given by a periodic. There is an addition of things apart from the free electron wave function. So e raised to ikr, that is a free electron wave function. So another one, there is an periodic terms that is, and because of this periodicity in the structure. So that is u of r. So this is actually called the block wave function. So when you put this type of wave function in your Schrodinger equation, and when you solve the energy eigenvalues, energy E value, you can see that energy eigenvalues are also varying periodically with respect to the wave vector. That is the energy eigenvalues are varying periodically with respect to wave vector. So this is for n equal to 1, the next level is n equal to 2, n equal to 3, n equal to 4, etc. So this is the same of that of previous concept, the splitting of energy levels. So here, because since it is periodic, no need to consider the complete structure, complete periodic arrangement. So only you need to consider the region between these minus 1 by 2a and 1 by 2a. That is, here the axis is k by 2 pi. So this region, we can put it as minus 1 by 2 a to 1 by 2a. So this is actually called it as the Brillouin zone, the first Brillouin zone. So no need to consider the complete region. So this is the thing. So in the region, first we can see that the width of these energy level is corresponding to the valence band, and the second next higher energy level corresponding to the conduction band, and there's higher energy bands, etc. But you can see electron in the first two energy levels. That is why people are considering only the first two energy level, only first two bands. Okay, so that is the concept of bands. Now, depending upon the position of the curve or the energy periodic arrangement of arrangement of energy eigenvalue, you can divide and you can classify the material into two types. That is direct bandgap semiconductors and indirect bandgap semiconductor. So the direct bandgap semiconductor is nothing but like this. So if the top of the valence band and bottom of the conduction band have the same K value, so if they lies in the same K value, then such material we call it as direct bandgap semiconductors. So some examples are gallium arsenide, gallium nitride, zinc oxide. So these are called direct bandgap semiconductor, whereas indirect bandgap semiconductor. So here the top of the valence band is here, and the bottom of the conduction band is here, some other point at some other K value. So here this is at a particular K value, and this is at another K value. So there is a separation. So this type of thing, material, we call it as indirect bandgap semiconductor. So examples are silicon, germanium, aluminum arsenide, etc. So now another point I have to mention here, it is a density of states. So you can see the large number of energy states. So the number of energy states available per unit in energy interval per unit volume is actually corresponds to the density of states. So density of states is nothing but the formulas are given by like this. So this is a bulk semiconductor or bulk material. So what is mean by bulk means the electron or carriers can move all three dimensions in freely. Okay. So if you consider x, y, z coordinates, so electron can move all the direction freely. Such material we call it as bulk semiconductors. So another one is the quantum well structures. So if there is a confinement along one direction, that means x and y direction, if it has a free movement, but if there is a confinement along the z direction, such structure we call it as quantum well structure. And quantum wire structure means if the confinement is along two directions, suppose y and z direction there is a confinement, and the x direction there is a free movement of carriers. Such structure we call it as quantum wire structure. And the next one is a quantum dot structure. So all three dimensions, if there is a confinement, there is such structure we call it as quantum dot structure. But here, so there are equations corresponding to that, the density of states corresponding to each type of confinement. So bulk material, there is no such confinement. So I'm most interested in this particular thing, bulk material. So the bulk semiconductor, so the density of states is given by this particular thing. Now, what is the use of this density of states? So when you have the density of states tells about the number of energy states. So when you multiply the number of states with the probability of occupation, if there is any electron is there or not, if you check that thing, so it will tell about the carrier concentration. So it will give the carrier concentration in the semiconductors. So the probability of density of states multiplied by the probability of occupation will give the carrier density or carrier concentration. So in order to get the idea about the probability, so we use the statistical mechanics. There is a term called Fermi function that is given by 1 by e raised to e minus ef by kt plus 1, where ef, that will tell about the probability of occupation by electron in that particular energy level E. Okay, energy E. So the EF, where EF is called the Fermi energy, it is called the highest field energy level at absolute zero temperature. So at 0 Kelvin, we can see that when you put 0 Kelvin here, the probability is given by up to E equal to EF, there is a probability of finding an electron, and below, if the energy is higher than EF, there will be there won't be any electron in the system. So that means probability variation is given by up to E equal to EF, there is a 1, and less than greater than EF, there is a probability is equal to 0. Now, this is at absolute zero temperature, 0 Kelvin. Now, for any temperature at E equal to EF, when you put E equal to EF, this can be, its value is equal to 1 by 2. So for at any temperature, if you want to plot this is for at T equal to 0 temperature, when T equal to greater than 0 Kelvin, so the same Fermi function you cannot use at that time. So the Fermi function will smeared at that time. So the probability at E equal to EF, the probability is given by Fe, the probability that is given by 0.5, that is 1 by 2. So that is the Fermi function concept. So when you multiply the density of states with this Fermi function, then you will get the carrier concentration. So that is the thing. So before that Fermi function, I will tell about something more. So at a finite temperature, when you heat the semiconductor at a particular temperature, so electron will jump to the conduction band. So you can see some few electron in the conduction band, at the same time few holes in the vacant space, that is holes in the semi-valence band. So that is what here you can see a few holes in the conduction band and few electron in the conduction band and few holes in the valence band. So this will tell about the probability of occupation of electron. And the black portion, that is a very small portion, that will tell about the probability of occupation by holes. So if this is the thing up to this particular region, the red mark tells about the probability of occupation by electron. So the remaining, there is a 1 minus Fe. If this is completely Fe, means Fe is this one, and this 1 minus Fe will tell about the probability of occupation by the hole. Okay. Similarly, the red indicates the probability of occupation of the electron, and the vacant space will tell about the probability of occupation by holes. Okay. So that is the concept. Now, when you multiply, this is the density of states. You have the figures like this density of states for the bulk semiconductor. So how consider the bulk semiconductor, the density of states for the conduction band and the density of states for the valence band. Now, the same Fermi function, if you draw like this, and when you multiply the density of states with this Fermi function, you will get the structure like this. So this is some expanded view only. So you will get a region like this. So this is the carrier concentration. So this area under the curve will give the carrier concentration. Similarly, when you plot here the number of holes, that is the density of states in this region multiplied by this 1 minus Fe will give you a region like this. So this is the density of holes, or the carrier concentration and the hole concentration. So this is for an intrinsic semiconductor. So intrinsic semiconductor, you can see that the electron concentration and hole concentrations are same only. So that is why you have the same picture in this particular figure. Okay, now let us consider the other type of semiconductor, N-type semiconductors. N-type semiconductor, you can see large number of electron in the conduction, means majority carriers are electrons and minority carriers also. So Fermi level will be at that time is very near to the conduction band at that time. So the Fermi level will be close to the conduction band. So if you draw the same thing, this is the Fermi density of states, and this is the Fermi function. At that time, you can see more number of electron in the conduction band and very few number of holes in the valence band. So when you multiply this into this, you will get a curve like this, a structure like this. So if you consider the area under the curve, you will get that carrier concentration, that is electron concentration or carrier electron concentration in the conduction band. So similarly, this whole probability multiplied by the density of states will give the Hall concentration. So you can see the electron concentration is much higher than that of Hall concentration in case of N-type semiconductor. So this is a schematic representation of that carrier concentration. Okay. Now coming to the P-type semiconductor. P-type semiconductor, as you all know, the majority carriers are holes. So you can see large number of holes in the valence band. So here the Fermi function is very close to the valence band. So now when you multiply the same thing, that is density of states with the Fermi function, here you can see the probability of hole is much high than that of the probability of electron. So this is the probability and the density. If you multiply, you will get a structure like this. And from the figure, you can see that the Hall concentration is very high compared to that of electron in the type case of P-type semiconductors. Okay, so this is a schematic representation of different types of semiconductors, intrinsic and extrinsic semiconductors. So carrier concentration representation. Now coming to the different types of semiconductors, the first type of materials we call it as elemental semiconductors. So the as from the name itself, you can see identify the things semiconductor. That means the material itself is a semiconductor. For example, the silicon, germanium, tin, etc. These are some of the examples. So that is a semiconductor, elemental semiconductor. Next one is the binary semiconductor. So that contains two elements. So that means either one element from group 3 in the periodic table and one element from the group 5, so that it will form a octet. So that will form a closed shell and a stable state. So similarly, other combination is like a group 2 element and group 6 element. So in that way also it will form an octet, in that form, you will get a stable state. So some of the examples are gallium arsenide, zinc sulfide, indium phosphide. So these are called binary semiconductor. Now the third one is ternary semiconductor. So that contains 3 elements. That means either that contains 2 elements from the group 3 and 1 element from the group 5. Or other way, the 2 elements from the group 2 and 1 element from the group 6. Okay, see, these are the combination. So in that way, means either this is gallium and aluminum, both are from in the third group elements. So and arsenic is the 5th group element. So this is the ternary semiconductor, aluminum, gallium, arsenic. Okay. So another one, quaternary semiconductor. So as the name indicates, that contains 4 elements. That means 2 elements from the group 3 and 2 elements from the group 5. So similarly, other combination is actually like there's 2 elements from the group 2 and other 2 elements are from the group 6. So one example, there are the indium and gallium are group 3 element, arsenic and phosphorus are the 5th group element. So that can form a quaternary semiconductor. So these are the different types of semiconductors, and the ternary semiconductor and quaternary semiconductors are very useful for the semiconductor industry. For example, for the fabrication of LED, lasers, all the other kind of things. So these are all called the alloy semiconductors. So is there any difference between alloys and their doping? There is a term I mentioned is alloy semiconductors. So that I will come to in the next slide. So these ternary and quaternary semiconductors are also called the alloy semiconductors. So these can be used for the band gap modifications, and it is also used for the formation of lattice matched heterostructures. I will tell you about these lattice matched heterostructures in the coming slides. So first we will discuss the band gap modification. What is the purpose of this band gap modification? So as you all know, you are getting the light coming from a semiconductor is depending upon the band gap of the semiconductors. So if the band gap is high, means you will get an energy corresponding to that particular band gap. If the band gap is very small, means you will get an energy corresponding to that particular band gap. So the band gap, by varying the band gap, you are actually controlling the energy of the emitted photon. That means you are changing the emitted color. Okay. Color of the LED or whatever it is. So the band gap modification or band gap tuning has very high importance in the semiconductor industry. So for example, let us consider gallium arsenide system. So gallium arsenide, you can see this is the, what is that? The valence band, and this is the conduction band, and which are separated by a distance. We call it as distance of 1.42 electron volt. Similarly, all the material have direct and indirect gap. I'm not telling that is a semiconductor, indirect band gap semiconductor, but all the material have direct gap and indirect gap. Suppose the direct gap is 1.42 and the indirect gap is 1.9 electron volt. A material is said to be direct band gap semiconductor by depending upon which value has the smallest value. So this is in here, the EG here it is 1.42 electron volt and the indirect gap is 1.9. So this is the smallest value. So this is a direct band gap semiconductor. Similarly, you can see aluminum arsenic. Aluminum arsenic, the direct gap is this one, 3.02 electron volt, and indirect gap is 2.17. So this is the smallest value. So this is a indirect band gap semiconductor. Now I am going to replace this gallium, some of the gallium with aluminum. Okay, so you are changing the environment in the crystal structures. So naturally, the electrostatic field and the distribution of the atom will change. Naturally, the allowed energy level will also change. So as a result, the band structure will also change at that time. So this is the thing, when you change, when you add or when you replace the gallium with aluminum, initially you have when X is equal to 0, that is the gallium arsenide itself. So the band gap is 1.42 and the indirect gap is 1.9. Now, when you change 20% of gallium with aluminum, you are actually changing to this one. So the band gap is changing, and now the band gap is a little bit high now, and the indirect gap is like this one. So next, when X is equal to 0.4, this is the band structure. And when X is equal to 0.6, like this. When X is equal to 0.8, you can change the band structure again. When X is equal to 1 means that is completely aluminum arsenic. So that finally you will get a band structure like this. So you are converting from this to this, and naturally here you can see the band gaps are varying. So as a result, this is the initial band gap. Now when X is equal to 0.2, this band gap is increased and like that. So when you plot the curve, the gallium arsenide in the other side it is aluminum arsenic. When X is equal to 0, that is gallium arsenic. When X is equal to 1, that is aluminum arsenic. That is the dark line indicates the direct band gap variation, that is 1.42 to 3.02. The band gap varied from 1.42 to 3.02. And whereas the indirect gap changes from 1.9 to 2.17. So you are actually changing the band gap of the semiconductor by simply adding the other materials. So in gallium arsenide, if you add aluminum, you are actually changing the band gap. So in that way, you can control or you can tune the color of the emitted photon. Okay. So that is the one technique. What is the use? That is the use of the ternary and quaternary semiconductors. So next one, that is what I said, doping and alloying. There is a difference. So doping, you all know the substitution elements are from the adjacent group. For example, if you want to make a N-type semiconductor, you are going to add the pentavalent impurity into the fourth group element. If you want to make a P-type semiconductor, you are adding trivalent impurity to the fourth group element. So these adjacent elements from the substitution elements are from the adjacent group. But in the alloying case, the substitution elements are from the same group. That means gallium you are replacing with aluminum only. Okay, here the conductivity is changing. In the case of doping, the conductivity is changing, but here the conductivity has a very little change, but the main thing is the band gap changes. Okay, and another thing is the doping concentration is very small, but in the case of alloying, you can see the concentration is very large. The alloying concentration is very large. So that is a difference. So next one, before discussing the concept of lattice matched heteros junctions, I will tell about different types of junction. So there is a concept of homojunction. So homojunction is the junction between two regions of different doping concentration. That means simply the junction between N-type and P-type of the same material. Okay, suppose there is a N-type silicon above which if you deposit P-type silicon, such junction we call it as homojunction, or N-type gallium arsenide and P-type gallium arsenide, if you make a junction, such junction we call it as homojunction. So on the other hand, heterojunction is the junction between two regions of different band gap or composition. That means for example, on the top of P-type silicon, if you are depositing N-type gallium arsenide, such structure we call it as heterojunctions. So these are the junctions case, homojunction and heterojunction. Then how one can fabricate this type of semiconductor or a junction? Okay, so the method we know. Hello, issues. Okay. So mainly there are two types of techniques. There are diffusion techniques and epitaxial method. So diffusion technique means that is if suppose I want to make a silicon means gallium arsenide on the top of the silicon. So you deposit this gallium arsenide when on the top of the silicon, and when you heat it at high temperature, the gallium arsenide or the material will diffuse into the other material. So you will get a structure like this. You can see in there is a curve like this. So that means the material is diffused into the other substrate. So such technique we call it as diffusion techniques. And epitaxial method is nothing but a layer by layer growth. On the top of the one layer, you are going to deposit another layer. So such structures are we will get a homojunction or heterojunction, whatever it is. So that is a layer by layer techniques. That is epitaxial techniques. Now, next term is called the lattice matched epitaxy. And as you can see, that is if you want to fabricate a good device, you need to make a defect-free structure. So what is mean by defect-free structure means here there is suppose there is a layer that having a lattice constant of AS and another layer that have a lattice constant of AL. And now you are going to make a junction between these two. Now you can see if the lattice constant of the first layer and suppose the lattice constant of the other layer, they are equal, and it will form a perfect bonding structure. So that type of structure we call it as lattice matched heterostructures or lattice matched epitaxy. Okay. Now suppose if they are different, that is lattice constant of the first layer, or normally we call it as the substrate, and the next layer is first layer. If they have different lattice constant, you can see when it make a bonding, is some of the atoms do not make any bonding with the other atoms. So that means the electron in this particular atom have different energy correspond than that of the electron in these particular other atoms. Okay. So these have already completed their bond, but this atom, the electrons are free, and so the electrons in this particular atom have different energy levels. So this will make and these type of bonds we call it as dangling bonds. Okay. So this will give some energy level within the band gap. So the strap, this is called the dangling bond. That is, electron in this particular atom will make an extra another energy level within the band gap, and that we call it as trap state. Trap state. So like that is just like a trap state increases the non-radiative recombination. What is mean by non-radiative recombination? I will tell you. So there is two types of recombination, that is a radiative recombination and non-radiative recombination. Suppose there is an electron in the conduction band. Suppose this is the electron in the conduction band, and that comes to the valence band with an emission of the photon. Such radiation we call it as, or recombination we call it as radiative recombination. Suppose instead of that, suppose if there is a trap state means will make a energy level within the band. So this is the energy gap within the band gap. There is an energy level that we call it as trap state. Now there is a same case, same way electron is in the conduction band, and that will make a transition to the defect energy level or trap state without any emission of a photon, and through phonon it will come to the trap level. And finally, again, it will come to the bottom of the conduction, top of the valence band with an emission of the phonon. That means phonon means they are that giving some heat energy to the lattice system. So such finally you are not getting any photons. Instead of you are getting some phonon, some heat energy. So such structure, such recombination, we call it as non-radiative recombination. So even if the materials are very perfect, the two layers, so suppose the first layer and second layer, even if they both are very perfect, very pure, if their lattice constants are different, you will get some dangling bond. Finally, that will result some non-radiative recombination. Suppose if this combination that you are making for an LED or laser, you will not get any light. So that is our first concept, lattice matched heterostructures. That is the importance of lattice matched. Okay. Now, suppose here, this is at one spectrum, showing the lattice constant, and y-axis there is a band gap. Now, suppose here you can say the lattice constant of gallium arsenide is almost same that of aluminum arsenide. So when you deposit gallium arsenide on the top of the aluminum arsenide, they are actually lattice matched. So you can deposit this gallium arsenide on the top of the aluminum arsenide. And similarly here, these line represent actually here it is gallium arsenic, and here it is indium arsenic. So the gallium is completely replacing with the indium. So this line represent Indian gallium arsenic, some composition of indium, some composition of gallium. And this point is actually 0.53 of indium and 0.47 of gallium. So this point, this is actually is lattice matched with indium phosphide. Okay, so this is a variation. Okay, aluminum gallium arsenic, and this variation is actually gallium arsenic, and finally you are making to aluminum arsenic. So this line represent aluminum gallium arsenic, and this line is actually represent Indian gallium arsenic. So this is the thing. So here this in indium 0.53 gallium 0.47 arsenic is in lattice matched with indium phosphide, and this is also a variation indium gallium arsenic phosphate. So you can see the gallium arsenic is lattice matched with indium arsenic, and these are the commonly used material for the fabrication of LED. And now this one, that is indium 0.53 gallium 0.7, is lattice matched with the indium phosphide, and that is the material used for the photodetector fabrication. And another one, this one is the Indian gallium arsenic phosphate is lattice matched to indium phosphide. This is also lattice matched to indium phosphide, and this is the commonly used material for the laser diodes. So that is the point I want to tell. If you want to fabricate an LED or laser diode, whatever it is, you need to consider the material that having same lattice constant of that of the substrate. Otherwise, you will get some defects, and that will lead to some bad performance in your device. Okay. So this is called the lattice formation of lattice matched heterostructures. That is the advantage of the what is that ternary and quaternary semiconductors. Now, as I said, if they have different the lattice constant of the layer and substrate, if they are different, that will lead to some trap state and dangling bond and trap state, and you will get a non-radiative recombination. But if the thickness of the layer, if it is very small, or if the I can say that okay, if the thickness is less than some critical thickness, so then this atom will rearrange, or atom will adjust by themselves like that. The atom will compress or by elongating. That will make a complete perfect bonding structure like this. So that means when you are making a bonding with this structure, heterostructure, with whatever it is like this, that the atom will adjust by themselves. That means if there is a compressive strain along one direction, there will be a tensile strain along the other direction. So there will be a compressive and tensile strain will be there. So such things will happen only if the thickness of the layer, if it is less than some critical thickness. So that critical thickness is given by this particular formula, the sub AS, that is the lattice constant of this substrate divided by 2 epsilon, where epsilon is the mismatch parameter. So if for example, if AS is this one, if the mismatch parameter is 1%, that will a thickness of 250 angstrom. So you can deposit 250 angstrom without making any lattice. You can make a perfect structure. So that means there is no lattice mismatch at that time. So if the mismatch parameter is very high, that is 10%, you can the critical thickness is only 25 angstrom. So that you can deposit only 25 angstrom. So 25 angstrom means that is in the order of 2.5 nanometer. Is there any structure that having in the order of 2.5 nanometer? And there are structures, and such structures we call it as quantum well structures. I have already mentioned what is meant by quantum well structures. So in quantum well structure, you can deposit 2 nanometer, 3 nanometer, 4 nanometer, etc. So that means there are structures available with this thickness, that is 2.5 nanometer or like that. So this is a typical example only. Similarly, that depends upon the lattice constant of the substrate. Okay. So that is we call it as strain layer epitaxy. Okay, that is a quantum well structure. I have given the picture only. Okay. Now, so far we have discussed the different concept of semiconductor material and their properties. Now, the semiconductor material as such of not so many practical applications, and mainly you don't have any control over the conductivity, real-time control over the conductivity. And even, for example, if you want to, the semiconductor, if you want to change the conductivity, means you during fabrication only you can change the conductivity by doping more impurity into the system. But if you need any real-time control over the conductivity, people will go for the PN junction, and that is the main most of and the component of any semiconductor devices. So as you all know, there is a p-type and n-type semiconductor. P-type semiconductor, the majority carriers are holes. N-type semiconductors are majority carriers are electron. Now, just I'm giving some idea about the different types of fabrication that I already mentioned. There is a diffusion of dopants, and similarly there will be an ion implantation technique, that is ion beam containing the dopants can be implanted into the substrate, thereby you junction. So diffusion and ion implantation will give you a graded junction. Whereas the epitaxial techniques, you are depositing layer by layer, you will get a abrupt junction. Okay, so these are the the techniques, and based on the techniques, you can divide into graded junction and abrupt junction. Another thing is that there are different types based on the other structure. You can classify this as homojunction. Already we have mentioned that is if the junction between, for example, n-type silicon and p-type silicon. Heterojunction means a junction between two different band gap material have two different band gap, that is a silicon and gallium arsenide. And another one is a Schottky junction. Schottky junction means a junction between a metal and a semiconductor. You can see in order to take the connection, you are normally taking one metal contact. So that junction we call it as Schottky junction. Okay. Now let us consider something about the band structure. So there is a band bending is there. How the electrons are moving from one end to another, such thing. It's a simple +2 class topic only. So this is a p-type semiconductor and n-type semiconductor. In the p-type semiconductor, Fermi level is very near to the valence band, where n-type semiconductor, the Fermi energy is near to the conduction band. Suppose these are the things before contact, but after contact, here the majority carriers are electron, and here the majority carriers holes. So when it make a contact, there is a difference in the carrier concentration. So the electron will move from one end to the another, and holes will move from one end to the other end. So as a result, this is what we call it as the diffusion of the carriers. So as a result, there will be a positive immobile ion will be created in the n-type region, and negative immobile ion will be created in the p-type region. And this is what we call it as depletion region. So as a result, there is an electric field. There will be a drift current as well. So the drift current will be there. So at an equilibrium stage, the diffusion current and drift current and the magnitude will be same. So that is, you can see there will be no such flow of carrier from one end to another. Okay, that means there will be the equilibrium stage. So that means it will happen only if the Fermi function aligns. Aligns. So if there is any Fermi function is constant, there will be no further flow from carriers from one end to another. So that means, so in order to make this Fermi function aligned, the band has to bend. So in which way the band has to bend, that I'm going to tell now. So this is the thing. So there is a p-type semiconductor and n-type semiconductor. This is the negative mobile ion and there is a positive mobile ion. Now suppose if you consider the charge density or rho. So this is like here it is negative axis. So this is the negative immobile ion and this is the positive immobile ion. So that is in the positive axis. Now, you know the electric field is given by E equal to 1 by rho epsilon into rho epsilon, rho of x into dx. That is the integral of the charge density. So if you integrate this complete region, you will get the electric field region. Okay, so integration means the successive addition of the thing. So when you add, you will get this. When you add this, keep on adding, you will get this increase to this value. And now up to this, you are but this is in the positive region. Again, you are keep on adding, then this will reduce, and finally you will reach a region like this. So this is the variation of the electric field. Now, from the electric field, you can calculate the electric potential. V is given by minus of integral E dx. So again, you integrate the electric field and there is a minus sign. So when you integrate this one, you are keep on adding this. So there is a minus sign here. That is why this is in the positive region. So again, you are adding and keep on adding, and finally you will get this thing. And this is the variation in this particular the potential. If you know the potential, you can calculate the potential energy. Potential energy is minus E into V. There is a constant minus some constant into V. So there is a minus sign here. So this is in the positive axis, that will come in the negative axis. So this is the variation of the potential energy. Now, what you are going to normally we plot is the energy axis, that is E versus K, like that. So energy versus position or something like that. So this is the complete structure at that time of equilibrium. So this is the band bending corresponding to, so the band bending is like this from upward to downward. So this is the band bending in the case of conduction band. Similarly, the band bending will be there for the valence band, and that will reach a equilibrium stage. That means, so now you can see the Fermi level is almost have a constant value, so that aligns. So this is the way of band bending in the case of semiconductors or p-type p-n junction. Now coming to the cases of positive bias and forward bias and reverse bias. What happens when you forward bias? So when you forward bias means same thing you can see. So the depletion region width will reduce. Like this, the width is decreased. So same way you can calculate the electric field and potential and energy. Now as a result, this bending is actually decreased. So at the time of when you forward bias, so the small bending. So the previous one is the without biasing, and when you forward bias, this is the bending. So what happens when you forward bias? There is a small bending. So this will go when you forward bias. This level is just little bit raised. So that means electron will go up. Electron will go up means that can flow very easy through this particular one end to the another. So the electron goes up means the electron can move free to the other end. So that means an easy flow of electrons. That is why you can see that when you forward bias a p-n junction, you are getting a very good flow of current. Okay. And at the same time, when you reverse bias, what happens? The depletion region width is increased. So that means when you can see the potential energy variation is this one, but the energy variation is little bit high. The energy bending, band bending is a little bit high. So that means the energy level is lowered at that time. So when you consider that time, so the energy level is lowered means this level is coming down. So that means electron is just is coming to the our side. So it cannot move from one end. At that time, electron cannot move from one end to another because the electrons are already trapped in this particular region. That is why you are getting very low current in the reverse bias case. That only the current is due to the minority carriers. So that is the reason for this particular characteristics, that the p-n junction characteristics. Only in the forward bias, you will get a very good flow of current, and the reverse bias, you will get a very small amount of current. Okay. So that is the p-n junction characteristics in terms of the figure. Now coming to the heterostructures. So far I have discussed the case of both have same band gap. Okay, the p-type semiconductor and n-type semiconductor have the same band gap. Okay, such structure we call it as homo junction. Now let us consider heterostructures. So what happens when you make a contact? So same way, I can show you that this is an N-type semiconductor having a band gap of this one, and the next one is a P-type semiconductor having a lower band gap. So this is the thing. Now that means there is a difference in the band position. There is a delta IC. There is a change in the valence band and conduction band, and change in the valence band. Okay, so there is a separate difference. So the band discontinuity is there. Now, same way, if you make a band Fermi level alignment, it has to bend like this. So it will bend like this. Okay, it will bend like this. So the bending will be, if you draw like in the previous way, you can see the band bending will be like towards upward. But there is a discontinuity. You need to consider that discontinuity while drawing the band bending. So that is what you can see here. Even though the band bending is in the upward direction, but there is a drop of conduction band, or there is a decrease in the band gap. There is a small thing that is towards the downside only. So that is why there is that delta EC is coming towards the bottom. Again, the next remaining portion of the band bending. So in complete, if you consider the total thing, this band bending is towards upward, but you need to consider that band and discontinuity, that is delta EC. Similarly, you can see the valence band. So initially the band bending is towards the opposite on the upward direction, but there is an upward movement of delta EV. So that you need to consider here. So this is the band bending in the case of a heterojunction. So this is the band bending in the case of heterojunction. Okay, now I'm going to tell about something about Schottky junction. Okay, as I said, it's a junction between metal and semiconductor. So it can be either a rectifying contact or an ohmic contact. So mostly these, you are taking the connection to this PN junction with some kind of some metal, some aluminium or gold or aluminium, silver, etc. So such junction we call it a Schottky junction. So I'm going to tell about what is meant by rectifying contact and ohmic contact. So rectifying contact, or sorry, first I will tell about the ohmic contact. Ohmic contact means that obeys the Ohm's law. That is, current is directly proportional to the voltage. So that means it follows a particular straight line thing. That is ohmic contact thing. Now rectifying contact. Rectifying contact that means that follows the diode characteristics. That means on the forward bias region you will get a good amount of current, and the reverse bias you will get a very low amount of current. So that is the rectifying contact. And there is a Schottky contact. Schottky contact means that is similar to that of a rectifying contact, but the upward movement means rise is little bit in the below region. So this is almost similar to the rectifying contact, but here also lowering at a particular lower voltage value. So this is the rectifying Schottky contact, and there is a near ohmic contact. That is not exactly forward by a good amount of current. But in rectifying and Schottky contact and normal rectifier, you will get only in the forward bias, you will get a good amount of current, and the reverse bias, a very low amount of current. Okay. Okay, so that is the thing. Why you can see in most of the optoelectronic devices, whatever LED, laser, whatever it is, you can see apart from normally they will not take any contact from layer and N layer. Instead of that, people will take the contact from P plus layer and N plus layer. What is meant by P plus means that is heavily doped semiconductors. That means normally there is a particular doping concentration. Now, if you increase the doping concentration, that is whole concentration, such that is we call it as P plus. And similarly, when the electron concentration is very, very high, such we call it as N plus semiconductors. So normally in the devices, you can see the people are taking contact from N plus and P plus. And why we can see otherwise when you are taking the P and metal, that will be some rectifying, that will be similar to that of a rectifying Schottky contact. I will come to the characteristics now. Now there is a junction here now. there is a N plus junction and P plus junction here. So another thing, P plus and metal and N plus and a metal. Now let us see the characteristics of that thing. So N plus and N junction is there. So this is the before contact. This is the two junctions before contact. These are the two material band diagram. Now after contact, this will make a band structure like this. Now what happens when you forward bias? For example, forward bias means I'm just giving this is to the positive side and the other end to the negative side. So when you forward bias means one end will go up. So this level will go up means the electron will jump from this to this. So that means the electron can move freely to this side. So that means you will get a very easy flow of carriers at that time. So now when you reverse bias, so when you reverse bias means this level will come down. So at that time, this electron will move to this side. So in that way, when you reverse bias, the electron will move from here to here. When you forward bias, the electron will move from here to here. That is an easy flow of carriers. So that is what here you can see is N plus and N junction is an ohmic contact now. Similarly, you can see the P plus junction. So at that time, hole movement, you can see when there is an upward movement and downward movement, there is an easy flow of holes. So that is what you can see the P plus junction is an ohmic contact only. Okay. So another one before that, okay, metal and semiconductor junction. Now there is a metal and the metal, there is a separation between the metal Fermi level and the top of the that is vacuum level. We call it as a work function. And here there is a electron affinity, that is a separation between vacuum level and the Fermi level, that is a Fermi function that we call it as electron affinity. Now as an N-type semiconductor is making a contact with the metal surface. At that time what happens? So here there are large number of electron and here there is a up to Fermi level there is an electron. Okay. Now when it make a contact, the band, similar to the previous case, there will be a band bending like this. And this separation distance, we call it as Schottky barrier height. Okay. Now, what happens when you forward bias? Forward bias means this will go up. That means like this negative side you are connecting to side. When you increase the voltage thing, this one will electron will move upward and that will flow to this side. So it can take to the other region. So that is an ohmic contact only. But when you reverse bias, what happens? This will come down. That is, when this come down means there won't be any movement of carriers, and there is a separation between these band bending is very high, so electron cannot tunnel through this as well. So the current will be an rectifying contact. So only in the forward bias you will get a good flow of current, but in the reverse bias you are not getting any flow of current. Very little amount of current due to the minority carriers. But what happens when it is an N plus semiconductor? So at that time, the band bending will be not that much. The thickness of this barrier is not that much wide, because during the junction region, the carriers will be diffusion will take place from the junction region only. So at that time, the width of the barrier will be not that much wide. So during the forward bias, similar to the previous case, the electron will jump to this one. You will get a ohmic good flow of carriers. But in the reverse bias, even though the carriers are coming down, there is a probability of tunneling current. The electron can tunnel through these barriers. So since the width of the barrier is very small, so that is why you are getting a good flow of current in the reverse bias as well. So in both cases, you are getting a good flow of current. So that is why people are using N plus semiconductor and metal contact. In the previous case, there is a metal and a semiconductor, means only in the forward bias you will get a current, and the reverse bias you won't get any, very little amount of current. So you cannot capture the complete characteristics of the PN junction what you are going to study. Okay. So that is the thing. Now coming to the LED concept. So LEDs are simply a PN junction device. So when you forward bias the PN junction, the electrons and hole will be recombined at the junction region. As a result, you will get the photons. That is the simple working condition principle of the LED. So now but when you are using the normal P-type material and N-type semiconductor, and you make a P-in junction, and when you forward bias, you will get this type of light. But it has a lot of disadvantages. I will tell you what are the different disadvantages. One is the reabsorption of the photon. Suppose the electrons and holes are recombined in this junction region, this photon will move in all the directions. It will propagate in all the directions. Suppose if the light is propagating in this direction, and electron in this p-type region, suppose it's moving towards the p-type region, an electron in this p-type region can capture the particular light, and it can jump to the conduction band again. Okay, so that means there will be a jumping of electron from the valence band to the conduction band, but actually finally you are losing one photon at that time. So that is a one log. So one photon you are actually losing in that way. Similarly, the other photon, if it moves towards the other region, and it can capture by the other electron in the system. So that is, we call it as reabsorption of the photons. Second one is the loss of the air semiconductor interface. Now the same photon, if it reaches suppose other photon, if it reaches the semiconductor and air interface, finally it has to go to the air only. So if it reaches the semiconductor air interface, you all know when a light touches the one medium having a refractive index of 1 and another having a refractive index of n2, some of the light will be reflected back and some will be transmitted to the system, the other media. Okay, so the reflectivity or the percentage of reflection is given by this particular formula, n1 cos theta 1 minus this n2 cos theta 2 divided by n1 plus n2, n1 cos theta 1 plus n2 cos theta all square. This is the reflectivity. Suppose if the material is your gallium arsenic and the where refractive index is 3.4 and air is the other medium where the refractive index is 1. Now even at theta is equal to 0, the reflectivity is 32.32, that is 32%. So the reflectivity is 32% when the light falls on the even at normal incident, 32% is being reflected back to the semiconductor media itself. So you are actually losing that 32% when it touches the semiconductor air interface. So that is the second loss. And third loss is total internal reflection loss. You all know total internal reflection means when the light passes from denser to rarer media, there will be a total when the angle of incident is greater than critical angle, there will be a total internal complete light will be reflected back. So theta critical angle is given by this particular formula, and when you if it is a gallium arsenide and air, the 16 degree is the critical angle. So if the angle of incident is greater than critical angle, that is 16 degree, the complete light will be reflected back to the semiconductor system. So that means that is a complete loss of the emitted photon. So people will not use, or commonly use some other structures for the fabrication of LED. So that is called the double heterojunction structures. So what is meant by double heterojunction? It's nothing but you have two heterojunctions. That is one here and another here. So normally this is the thing. So 3-layer system, and that is, it have a sandwich structures. So in the middle material have a band gap of low band gap, and the other two material have low wide band gap semiconductor. So this is the double heterojunction. If you make in this way, you can overcome some of the difficulties. Okay. So for example, yeah, again I can just draw the band diagram here. So suppose this is a P plus aluminium gallium arsenide and P gallium arsenic and aluminium gallium arsenic itself N type. So this is this is the middle material, we call it as the active material, and the other two are the barrier layers. So such thing. So same way you can draw the band diagram. So initially before contact, this is the band diagram, and after when you make a contact, finally you can see this is the band diagram. So now when you forward bias, that means when you give a negative bias to here and a positive bias to here, means this level will go up. That means the electron will jump into the middle region. It cannot jump to the other higher region because of that have higher energy. Similarly, these holes will move into the, if it come down means, if one side it will go up, other side it will come down. That means the hole will move to this region and it will be trapped inside the middle region. It cannot come to this particular bottom level because holes will always occupy on the top of the band, and electron will occupy in the bottom of the band. Okay, it's just like a water drop. Water drop you can consume as an electron. It will always come to the bottom, and the other one, water bubble, you can consider as a hole. So it will always occupy on the top of the band. Okay, so the hole will occupy on the top, and electron, it cannot jump to the other one. Hole cannot move to the other way. So it's just like a trapping of electron in the conduction band of the middle region, and trapping of holes in the middle region, active region. So that means even if you give a very small amount of current, the electrons are trapped, holes are trapped inside the region. And now they can combine together, and they can recombine, the electrons and hole can recombine each other, and you will get a photon, that is an emission. And that is the concept of double heterojunction based LED. Now, so if you are considering double heterojunction structures, there won't be any reabsorption losses, because the middle band material have a band gap of this one small band gap. Even if it passes through the other, propagates to the other region, it cannot absorb, means other electron in the other region cannot absorb that particular photon, because the energy of this emitted photon is less than that of the band gap of the that particular material. So it will not absorb. So there won't be any reabsorption of the losses. Another one is the carrier confinement. As I said, when you forward bias, the electron will be trapped inside the middle region, and holes will be trapped inside the middle region. There is a confinement, a carrier confinement. As a result, even if you give a very small amount of current, large number of carriers will be trapped inside the region, middle region. So in a small region, if there is a large number of carriers, means the carrier density will be very small, and the gain of the such medium will be very large. So that is why these type of structures are commonly used for the fabrication of LEDs in these days. That is double heterojunction based LEDs. Apart from that, there is another concept, that is optical confinement. So here we have used aluminum gallium arsenide and aluminum gallium arsenide structure. So here the gallium arsenide have low band gap, that material have high refractive index. So this is the refractive index of gallium arsenide. Aluminum gallium arsenide has a refractive index, lower refractive index. Now when the light passes, so middle region is gallium arsenide, the refractive index is high, and other region the refractive index is small. So actually the recombination is taking place in the gallium arsenide, that is the middle region. If the light propagate in all the directions, so for example, the light, when it touches this media, if the refractive index of this media is high than that of the other region, so if it is greater than critical angle, that will be reflected back, again reflected back, like that it will come, and finally that will be ejected through the sideways. And that is the concept of another one type of LED. We call it as edge emitting LED. And there are one more other type of LED that is a commonly used LED structure, that is a surface emitting LED. That is the this left side figure, that is a surface emitting LED, and the other one is edge emitting LED. The commonly used LED is actually the surface emitting LED. So you can see there is a transparent window will be there. So in the active layer, that is P plus, this is N plus, sorry, this is N plus only. So in the middle region, the active region, that is in the middle region, the active region, there will be a photon emission that will propagate in all the direction. And here there is an opaque region, because there is a metal here. So a light will not come in this direction. Only it will come in the upward direction. So that will you can extract the complete light through this particular window, transparent window, and that is the normal LED, what you are seeing in the lab and everything. That is a surface emitting LED. And but there are other type of LED that I mentioned in this previous concept. That is if the refractive index is higher, low, middle region is higher than that of the other barrier layer, the light will be pass through the edges of the LED, that is through the edges you will get the light emission. So such LED we call it as edge emitting LED. So edge emitting LED is commonly used for the communication purpose. If you need a very sharp beam of light, people will use the edge emitting LED, but it is a little bit expensive in the case of fabrication and all the things. You need to deposit this much number of layers. So this much number of layers, active layer N, P, and P plus and N plus, and then only you can take the metal contact. Okay, so these are the typical structure of an LED, and the last I can say, but you can see on the dielectric encapsulation on the top of the each LED in the lab and everything. You can see this type of LED structure. So that is actually this type of structure only. What is that? Sorry. This type of structure only. You are taking one contact from here and another contact from here. Okay. So that means when you are putting this thing, anyway, there will be a semiconductor and air interface. That means 32% of light will be reflected back from the semiconductor. So you're actually losing that particular light. So in order to reduce that loss, people will use this dielectric encapsulation. That is one use of the dielectric encapsulation, where the reflectivity is given by, first there will be a semiconductor and dielectric material, and that is junction, that interface. So at that time, that reflectivity is given by R1, and there will be a dielectric as well as air. That is the reflectivity terms corresponding to that interface, that is R2. So the total reflectivity is R1 into R2, that is given by 18%. Earlier it was 32%. Now it's reduced to 18%. Now another advantage of dielectric encapsulation is that to protect the semiconductor from the outside. So that is the use of the dielectric encapsulations. So this is the concept of double heterojunctions. So what I have covered is the fabrication of LEDs and the different concept of semiconductors and all the things. So with this, I am stopping on the topic of today's lecture, that is heterostructures. Oh, sorry, before that, I can just give you some the characteristics of LED as well. So this is the current voltage characteristics, similar to the for PN junction only. This is only a PN junction. So it follows the PN junction characteristics, and that is IV characteristics is similar to that of here. And there is a output power versus current. The power versus current, and the power is given by this particular formula, that is proportion to the current passing through the device. So there is two terms, that is eta E and eta I. That is extraction efficiency and internal count efficiency. There are two terms, so I'm not going to discuss this in detail. So when you increase the current, you can see the power output power is also increasing, and at particular region, when you increase the current again, there will be a saturation. There are reasons for this. When you increase the current, that leads to the joule heating in the system. That is, when you heat the current, when you give the more current, means the heat, the I square R term will increases. That means that will lead to the phonon emission. So as a result, there is a saturation in this particular light current characteristics. Apart from this, another one is the intensity distribution. Intensity distribution is given by this particular shape, and it is given by this particular rate of spontaneous emission is given by this particular formula. When you multiply the rate of spontaneous emission with the energy of the photon, you will get the power output, and with the unit area you will get the intensity. So this is a typical structure plot of the intensity distribution, and where the with the DAF maxima will tell you the focusing and nature of this LED, and typical the full width DAF maximum of the LED is around 20 to 25 nanometer, whereas in the laser diode the FWHM is in the order of 1 to 2 nanometer. So these are the characteristics of LED. So now 340, so 320. Now I can just give some idea about the work that I have carried on. Means we're conducting in our lab. So I'm mainly working on the two-dimensional material, and mainly on MOS2 semiconductors, and this is a typical SEM image of the semiconductors that were fabricated in the lab, and we have studied all the properties like electric, means what about the structural property by X-ray diffraction and the magnetic property as well as the photoluminescence. And it has a particular property that we call it as the upconversion photoluminescence. That means normally you can see the 440 nanometer, and then here the emission is 600 nanometer. So the energy of the excitation is around 440, but the energy of the emitted photon is less than that of the. That is a normal phenomenon. That is a normal PL. But here you can see the excitation energy is 795, but the emission is in the order of 520 nanometer. That is, we call it as a upconversion photoluminescence. That is a typical property, one of the important property of this particular material, a moist to nanoflakes. And after that, we have, in collaboration with some of my group here in Central University, with some work, biological work as well. So we have fabricated a MOS2, and that is encapsulated with a zinc oxide nanoparticle. So you can see the shape nanoflakes we attached with the zinc oxide nanoparticle, and you can see the XRD pattern that tells about the MOS2 as well as the zinc oxide nanoparticle. And we have studied the anti-angiogenic and anti-cancer properties of this thing, and we can see that this is the cancer cells. When you treat with the cancer cell with the MOS2 ZNO, that is this nanocomposite, finally you can see the size of this that cell is reduced, and we have checked all the other parameters like this enzyme, that is caspase 3 enzyme values, and you can also see the hemoglobin content here. This is the cancer cell, and here you can see there is no cancer cells. So a cancer cell cannot go beyond 1 to 2 nanometer if you are not supplying any oxygen to the system. But the oxygens the cancer cell is getting the oxygen through these blood vessels. So actually we are here, you can see there is no blood vessels, so that actually killing the cancer cells. Okay, now there is another parameter that is endothelial to mesenchymal transition. So this type of enzyme parameters we will check at that time. You can see that then this tells about the that is a cancer it will move from one part to another. So in order to check that property, we checked these parameters, and we found that there is no transfer of the cancer cell to the another parameters, okay, another region. So this is the one of the work that we have done in collaboration with the one of the biology group in here at the university. Apart from that, we have also fabricated some MOS2 based gas sensors. So this is a typical structure. We have fabricated the P-type silicon substrate. On the top of that, we have deposited silicon oxide, and there is an electrode, chromium gold electrode like this. And in between, we will deposit our MOS2, and when you pass the current, this is a typical device that we have fabricated in the lab. So when you pass some gas to the system, you can identify. We have checked several gases, and we found that this is not MOS2, this is not MOS2 palladium compound, palladium doped MOS2 samples. And here you can see these samples giving very high sensitivity to the NO, and we have checked the sensitivity towards the other gases like ammonia, H2S, NO2, etc. But it's showing very high sensitivity towards NO. And that is a selectivity. So this is selectivity properties. And next one, we have checked what are the different concentration, 2 ppm, 1 ppm, and shows a very good behavior. And this is the sensitivity part of the particular gas sensor. And later we checked the stability part as well. We did the measurement at a different time interval and showing almost a similar pattern. And that is the stability part of that particular device. And later we did some work is in the of the phase transition. That is, one is hexagonal phase to the octahedral phase, and normally this is a semiconductor nature and this has metallic nature. So we studied the electrical properties like IV characteristics of both system, and this is have another property like electrocatalytic. So hydrogen is considered as the green energy carriers, because the other one, the hydrocarbon economy, is have a lot of disadvantages. And because it need for normally the electrochemical water splitting is the best method to get the hydrogen. So for that you need a particular electrocatalyst. So normally platinum, such high costly materials are normally people are using, but instead of that, if you can replace that platinum with some sort of semiconductors or other materials. So we tried with MOS2 and we found some electrocatalytic property for that particular material. So this is the one other work that we have carried out in the last 2 years back. And we have also checked the photoluminescence in different media, and it shows that it is showing very good photoluminescence when you are dispersing that in ammonia media. So this can be used for some sensing of ammonia as well. Okay, so another thing, another material, another two-dimensional material that we are working here in my lab is SNS2 nanostructure. We have studied all its properties like electric structural, morphological, and all electric magnetic properties, etc. This is a typical SEM image, and we have also fabricated some junction with these particular silicon substrate SNS2, that is P-type silicon and N-type SNS2, and you can see a typical diode characteristics, and we shined with some light as well, so it shows some photocurrent as well. So this we have published in last year in Applied Surface Science. And this is also another type of material that WS2 nanoflakes, and we did almost all that similar type of work here, but different. But this is a different material, tungsten disulfide. And so these are the things. And one more is there, the vanadium disulfide. Here also you can see the sheet-like structures, that is two-dimensional structures of vanadium disulfide. And some of the work still doing some work of this one in the lab. And people have also fabricated then P-type semiconductor, P-type two-dimensional material. So the previous, all the material that are N-type semiconductor, now if you combine that N-type and P-type, then you can fabricate a complete 2D P-type PN junctions devices. So that is challenges. There are so many challenges in fabricating types of devices. So we are trying to make such devices in the coming days. So another one of my students is also working on the organic solar cells. So this is the typical structure of the organic solar cells, and we got an efficiency that is a P3ST PCBM based organic solar cell. We got an efficiency of 2.73%, and we studied almost all its properties. And we have also checked the plasmonic effects in the type of solar cells. That is when you add a gold nanoparticle to the system, what happens? The device performance also we checked. So we found that there is a 24% efficiency when you add gold nanoparticle into the systems. Okay, so these are some of the work, and we do a lot of work on the different semiconductors like TiO2, zinc oxide, MO3, nickel oxide, vanadium oxide, etc., etc. So many things, thin films of various oxide semiconductors. So these are the things, and thanks to you all, and acknowledge the collaborators, Professor M.K. Jayaram, and of Cochin University. Currently, he is the Vice Chancellor of Calicut University, and Professor Dr. T.N. Narayanan of Hyderabad, TA for Hyderabad, and Dr. Samir. I did the biological part with the Dr. Samir, and it's a faculty here in biochemistry, and Dr. Etre, and he helped me in the sensing part of my devices. And these are some of my students. Thank you all. So if there are any questions, I'm ready to.
Thank you, sir. Thank you so much. The session was very rigorous, and I think the participants have got a thorough understanding of the semiconductor electronics and the LED manufacturing, manufacturing of LEDs. Now participants can have their feedback, have their questions to Professor Aneesh PM. So participants could just please be hurried to ask questions to Dr. Aneesh PM. Please. I would like to welcome Professor Rafi from MES College of Engineering. If he is present, I think he would like to add more. It's been a long time, sir.
Thank you, John Paul.
Thank you, Rafi, sir. Okay.
Good evening to everyone. It is an honor to have been asked to offer a vote of thanks in this session. Dr. Aneesh, PM, Assistant Professor, Central University, Kerala, did this section in a wonderful manner. The session on basics regarding fabrication of LED was very useful. Personally, I am a mechanical engineer. I am actually not an expert in this field, but your basics regarding the LED fabrication was very useful to me. I would like to extend thanks, sir, and express my sincere thanks to the organizers for conducting a wonderful program in such a manner. Thank you.
Thank you.
Thank you, sir. Thank you, sir.
Thank
If
you.
any other participants need to add, they may please. If any of your questions need to be answered, those who want to know more about the research opportunities, please. Okay then. Okay, sir. So thank you on behalf of MES College of Engineering and from the FDP. Thank you very much for your session. Okay. Thank you, sir. Thank you, sir.
Thank you.
Okay, so what we are going to do, we are having a 15 minutes break, but we are not ending the meet. We will just have a 15-minute break for just refreshing, and after that we will start the session again. Okay, so don't break from the meeting. Let the meeting continue. Let the meet remain there. You can have a 15-minute break and come back. Okay.
കുറ്റിപ്പുറം MESCE എഞ്ചിനീയറിംഗ് കോളേജിലെ വിദ്യാർത്ഥികൾ രൂപകൽപ്പന ചെയ്ത സൈനിക വാഹനമായ ആയുധയ്ക്ക് ദേശീയതലത്തിൽ അംഗീകാരം. പ്രതിരോധ വകുപ്പിന് കീഴിലെ ഡിഫൻസ് റിസർച്ച് ആൻഡ് ഡെവലപ്മെന്റ് ഓർഗനൈസേഷൻ നടത്തിയ റോബോട്ടിക് എക്സ്പോയിൽ 1ാം സ്ഥാനം ലഭിച്ചത് ആയുധയ്ക്കാണ്.
ഞങ്ങളുടെ ഫസ്റ്റ് അയൺമെന്റ് സ്യൂട്ട് ജനറേഷൻ 1 ഡെവലപ്പ് ചെയ്യുകയും ചെയ്തു.
Okay, shall we see? Okay, shall we resume the session?
Sir, we can resume the session. Dr. Jayaram is online, so we can proceed.
Okay. So the next session will be handled by Dr. P. Jayaram. It's an immense pleasure to welcome Dr. P. Jayaram. Dr. P. Jayaram is a professor from the MESCE Kuttippuram College, and he has been a research guide to Calicut University, and he has been extensively doing research on the thin film solar cells. So on behalf of MESCE College of Engineering and from the Faculty Development Program, I invite you, sir, to the session. So Dr. P. Jayaram has published many books and has more than 20 journals to his credits. So I hope that the participants will be extremely benefited by his talk on transparent electronics, the techniques and applications. So, sir, please.
Thank you very much, John Paul. Thank you very much for the introduction. Dr. Sunish, thank you very much for inviting me to the FTP program. I also thank the other organizers, coordinators of the FTP program. Thank you very much. I was thinking, no, actually I was afraid that Dr. Aneesh is going to discuss all my slides. So it's a very closely related field like LEDs and transparent conducting oxides. Aneesh is there?
Yes, I'm here.
Okay. I was thinking that you are going to encroach into my slides. Thank you very much for not discussing elaborately about the transparent conducting oxides. Thank you. Okay, I think I can begin right now. I am sharing my slides. Okay, see, you can interfere at any time. If you have any queries, you can raise the hand or put a on-screen message. Okay, thank you very much. Let me share my screen. Hope you can see it, right? Hope you can see it, right?
Yes,
Yes, sir.
And I'm audible too, right?
You are audible and your screen is visible.
Okay, thank you. Thank you very much. So once again, very warm good evening to all of you. See, let me directly go to my presentation. See, this is my title of presentation. Actually, I have made a small correction in the title that is already published in the brochure. So I have changed. I am discussing the theory, techniques, and eventually the applications of transparent electronic materials. Okay, so let me directly go to the presentation. So let me introduce the material transparent conducting oxides to you, or let me introduce to the field of transparent electronics to you. I think some of you are familiar with the topic transparent electronics. For them, please excuse me for first few slides, and then we will go to the technical part of it. Okay, so what is transparent electronics actually? See, we know that we know about transparent material and opaque material and electronically conducting material. So as we know, the material that transmit the visible radiations are called as transparent material. For example, like glass, quartz, etc., are transparent material. And meanwhile, the material that does not pass light are called as opaque materials that does not transmit light. Okay, and you know that the transparent material like quartz, glass, etc., are insulators. They cannot conduct electricity. So you can see from the slide that the resistivity of glass and quartz are in the order of 10 to the power 17 ohm meter. And meanwhile, you can see the electronically conducting material. The electronically conducting material are mainly metals. So metals are highly conducting, but you know that metals cannot transmit electromagnetic radiation. And see, the resistivity of the metal falls in the order of 10 to the power minus 7 ohm centimeter, like that. So that means the material that transmit electromagnetic radiation cannot conduct electricity. And on the other hand, the material that conduct electricity cannot transmit light. So do we need a material that simultaneously transmit and conduct electricity? So that is our question. So transparent electronics comes under this category. So this is a contradictory material. We will call it as a contradictory material. So what is contradictory? So this is the contradictory fact that the transparent materials are insulating and the conducting materials are opaque. Okay, so we need to combine both these features like transparency, optical transparency, and electrical conductivity in a single material. Is that possible? That is our question. So it is possible. So what are the possibility of a special class of material, making special class of material? So that's all deal with the transparent electronics. See, by definition, what is transparent conducting oxides or transparent conductors? So most of the transparent conductors are transparent conducting oxides. So what is the speciality of it? So by definition, transparent conductors are a unique class of material that exhibit visible transparency of the solar spectrum and metal-like electronic conductivity. So transparent conducting oxides, by definition, it is a unique class of material. It is a unique class of material that transmit electromagnetic radiation. At the same time, simultaneously, it exhibit electronic conductivity. So typically, transparent conductors exhibit 90% of optical transmission to the visible radiation and electrical resistivity in the order of 10 to the power minus ohm centimeter. See, where we can find TCOs, or what is the advantage of making such a material? Where we can find TCOs. So we are holding a transparent conducting oxide material in our hand right now, a mobile phone. Okay, simplest example is a mobile phone. So a mobile phone, a smartphone, in fact, a smart mobile phone uses a display that is used as an interface between our command and the operation of the mobile phone, our command and operation of the mobile phone. So you want to use a mobile phone and you want to give command to the mobile phone. So how you are doing input to a mobile phone? So you are doing giving an input to a mobile phone by touching on the particular icon or folder. Like, okay, so you need to give an input to a particular folder. You will press it. So you want to see that folder. Sorry. So you want to see that folder and you want to give the instruction to that folder that open it. Okay, so you want to see it and you have to send a signal. So for that purpose, you need a material that is transparent as well as conducting. Okay, so for that purpose, on the top of a display, it uses a transparent conducting coating on the LED or LCD display of the mobile phone in order to send the message to the phone, to the phone. Okay. Similarly, all kind of displays, all kind of modern new generation displays of like television, and computer displays uses transparent conducting oxide. So it is an inevitable component of these devices. And similarly, one of the largest user of transparent conducting oxide material is a solar system, especially thin film solar system. Okay, so it uses a top conduct. It uses a top conduct as for the functioning of it. Similarly, automobiles and defrost windows, etc. It is widely using. It is a prominent material in our new day-to-day life. Okay, so we can find TCOs at everywhere. So let me explain the functioning of a TCO, candidature of a TCO in a device, say a solar system. Okay, so a photovoltaic system. As you know, photovoltaic cell is a PN junction. A photovoltaic cell is a PN junction. That means when the electromagnetic radiation falls on it, the electron hole pairs are generated and it will go to the external circuit, giving us the electricity. Okay, so in this case, see what we are using, a metal contact on the top surface of a solar cell. See, I am explaining about a thin film solar cell rather than a silicon first generation solar cell. Okay, so when we are using a metal contact on the top surface of a photovoltaic material, what happens? The light cannot pass through the cell. That means the light cannot reach the heart of the cell. In the heart of the cell, the electron hole pairs are situated, and the light need to liberate the electron from the hole pair. Okay, so if you use a metal contact, the light will reflect back and it will not give you any electricity output. Okay, so what we need a transparent conducting material on the top contact as the top contact. So what happens when light falls on it? When light falls on it, what happens? It will go into the heart of the solar cell and it will liberate electron from the hole pair, liberate electron, and it will move to the external circuit. So TCO can be used to carry the photo-generated electron to the external circuit, as well as simultaneously it can transmit the electromagnetic radiation. See, you can see the light can pass to the heart of the solar cell, and the photo-generated electron can be simultaneously transmitted to the external circuit. So TCO has got important application in photovoltaic industry, especially the new generation solar cell devices. So it is also a very important part of a photovoltaic system. So let me come to the theories of transparent conducting oxide. So this one Dr. Aneesh explained well, beautifully explained by Dr. Aneesh. So band structure, so you know that band structure. So band theory predict that there are three types of material like metals, insulators, and semiconductors. So why metals are conducting? Metals are conducting because it is having an overlapped valence band and conduction band, and it has large concentration of free electrons in the conduction band. However, insulators are non-conducting because there is a gap between valence band and a conduction band, that an electron can never excite from valence band to conduction band in an insulator. The gap is very large. On the other hand, we are having the third type of material called as semiconductors. So semiconductors generally the band gap vary from 0.7 electron volt to 3.9 electron volt. So that means there are some chances for an electron to excite from valence band to conduction band. Okay, and you know that there are such transitions are called as say intrinsic semiconductor and extrinsic semiconductor. And so intrinsic semiconductor, if we have a thermal variation or some thermal variation, or the material can itself jump from in a material, the electron can itself jump from valence band to conduction band. And extrinsic semiconductors are semiconductors that dope with impurities. So it is called as induced defects in a semiconductor. So there are possibility that a insulator semiconductor can be converted into a conductor by doing some manipulations on the material. Okay, so we have this class of material, and we are having the fourth class of material called as transparent conductors. But we need to be precise about it. Transparent conductors are not 100% optically transmittive and not metallic conductive. So metallic conductivity is approximately around 10 to the power -7 ohm centimeter, like that, and transparent conductors show its conductivity in the region of 10 to the power -3 to -5 ohm centimeter, like that. Okay, so how can we synthesize, or how can we develop a transparent conducting material, or how can we implement the same property like transparency and conductivity in the same material? That is our question. So fortunately, we are having some material called as metal oxides. Not all the metal oxides. Some metal oxides are highly transparent when it is deposited as a thin film, and some semiconductors are not highly transparent but moderately transparent, but the transparency can be improved by adding certain metals, certain impurities to it. Okay, so we are having some material like zinc oxide, tin oxide, gallium oxide, indium oxide, cadmium oxide, etc. shows this high transparency and moderate transparency, and in its pure state or undoped state, they are insulators with a band gap approximately around 3 electron volt. Okay, in its pristine state, like I will say, in the undoped state, it is having high band gap and it is an insulator. Okay, but the electrical properties of this material can be modified in a desired manner by adding certain amount of foreign impurities to it, foreign element into it. Okay, thank you. Is that okay? Yeah. Okay, so if we are adding some impurity into the host crystal matrix, what happens? The impurity can help you in increasing the carrier concentration, as well as it can make the absorption edge of the optical spectra into the ultraviolet region, that will result in increasing the transmittance of the material. Okay, so degenerate doping in this host material can at the same time be used to increase the conductivity and increase the transparency. How it is accomplished? We can see it. See, this is we called as the compositional space group, phase space of transparent conducting oxide material. I said like transparent conducting oxide material, but a few material, very small material. It's a very small group that exhibit transparency and conductivity, and these are those 4 pillars. I mean 5 pillars in developing transparent conducting material. They are indium oxide, cadmium oxide, tin oxide, gallium oxide, and zinc oxide. So these are the main parent material that is used to develop almost all the transparent conductors. I will say all the transparent conducting oxides, TCOs, are developed based on this material. Okay, so these properties, the material we are having for developing transparent conducting oxides, can be used to change the property by mixing each other or doping with another material. So like that. So the indium oxide can be doped into the cadmium oxide. The tin oxide can be doped into the indium oxide, gallium oxide into the zinc oxide, like that. So either mixing the materials together or doping together, the new material can be formed, and this material will show beautiful property like the high transparency and electronic conductivity. So you can see some examples on the left side of the screen. You can see that tin oxide can be doped with the antimony, fluorine, arsenic, etc., like that. Similarly, indium can be doped with tin, germanium, etc., and zinc oxide. Zinc oxide is a versatile material, so weak by using zinc oxide. Aluminium, gallium, etc. can be used as dopants. And another thing is, okay, I'm going to discuss it. So this is the compositional space group almost all the transparent conductors are developed based on this material, these 5 materials. So we are having different classes of material based on these 5 compounds. What are they? So metal oxides, the classification is mainly based on the number of cations used. Okay, based on the number of cations used, there are some different categories like unary oxides, binary metal oxides, multi-component oxides, and ternary oxides, etc. So what are these? Let me explain. So you know that zinc oxide, cadmium oxide, titanium oxide, etc. Some example are unary oxides that are undoped metal oxides, no modification, no manipulation done on that compounds. And binary metal oxides are called as the material doped with another compound. Okay, a foreign element is added into the crystal structure of the parent material. Okay, a foreign element is added to the crystal structure of a parent material. So here, if zinc oxide is the parent material, aluminum is doped inside it, and tin oxide into the indium oxide, like that. So that are binary oxides. Okay, and we are having the 4th category called as ternary oxide. Like, it is not doped, it is a new compound. But see, you can see that zinc oxide is not doped in, sorry, tin oxide is not doped in zinc stannate. It is a mixture of zinc oxide and tin oxide called as zinc stannate. Okay, cadmium stannate, etc. are some example for it. Similarly, we can have the 4th category of material called as multi-component oxide material. So what are multi-component oxide material? So we are having this material. So we are having some possibility to tune the material in a precise manner by changing the amount of number of cation and amount of cation. So you may have different cations like zinc, tin, indium, etc. in the same compound, and you will have the precise ratio of the cations in that compound. So you can tune the properties of the material in a precise manner by changing the values of cations, number of cations in this. So that is the 4th category of material called as multi-component oxide material. So what are the desirable features of transparent conducting oxide? You know that now we need green materials, so we don't need toxic materials. So that is one criteria. And green processing, cost effectiveness, availability, and easiness of deposition or application. So that are, say, general criteria of developing a transparent conducting oxides. And we have this optoelectronic criteria, that high visible transparency, very good electronic conductivity, high carrier concentration, high mobility, and high mobility with low carrier concentration, work function, etc. And the deposition should be easier. That is the main processing criteria. So we have some processing criteria for also there for the development of it. And these are some material shows highest transparency, highest conductivity, mobility, work function, etc., etc. So some material, some doped material shows high transparency. In another case, some binary compound shows high transparency and conductivity, like that. So it will vary from compound to compound. And these are some important material discovered in the field of transparent conducting, transparent electronics or transparent conductors. Okay, these are some general doping materials in TCOs. I think I can skip this slide. See, what are the properties of transparent conductor? What are the major property of transparent conductor? So as we know, the major property of the transparent conductor is its high optical transmittance. High optical transmittance and high electronic conductivity. So how can we measure the optical transmittance? This is the slide is showing a typical optical transmittance spectra of a Indian tin oxide. Indian tin oxide is the most important transparent conducting material. ITO, it is called as commercially called as ITO. Almost all the devices uses an ITO. ITO in your mobile phone, you can see ITO. In almost every devices, it uses an Indian tin oxide thin film on the top surface. So this is the typical optical transmittance spectra of an ITO. So you can see that the visible radiation is almost above 80 to 95% of the visible radiations are transmitted, and that shows very high optical transparency. It is recorded by using an UV visible spectrometer. So it shows a very high optical transmittance, almost 90% above light electromagnetic radiation is visible electromagnetic radiation is transmitted. Okay, so this is the typical feature of a TC, indium tin oxide, high transmittance in the visible region. Similarly, see, you can see in the right hand side the band structure of a normal material. So see, you know that see, for the simplicity we can assume the valence band and conduction bands are in parabolic shape, and say there is an energy gap between valence band and conduction band. So this is the first figure shows a normal normal band diagram of a host material, whether it can be tin oxide or zinc oxide, anything like that. A normal band structure of a host material. So what happens when we dope the material with a foreign element? What happens? The electrons will be the dopants will give a lot of electrons to the conduction band. That means for an electron, for a next electron to jump from its valence band to conduction band, they have to travel this additional distance. That means the free electrons in the conduction band shift the valence band and conduction band in the opposite direction, and that create an increase in the band gap of the material. And this shift is called as Burst-in-Mohs shift or Burst-in-Mohs effect, the increase in band gap due to the introduction of foreign elements into the conduction band is called as Burst-in-Mohs shift, and that will result in the expansion of the energy gap. So due to the expansion of the energy gap, the absorption onset will be shift towards the ultraviolet region, and you will get more transmittance. Okay, so the doping will result in increasing the percentage of transmittance. So the tin oxide, if tin oxide is moderately transmitting, if you introduce tin oxide into it, it will increase the transmittance of indium oxide. So indium tin oxide become more optically transmitting. So you know that, say, for almost all the applications, optoelectronic applications, we use a direct bandgap semiconductor. That means no phonon assistance is required for a transition. So we have to use the direct bandgap semiconductor for this purpose. Okay. So this band gap, how this band gap is generated? So this is the typical host, and this is the transparent conductor. So the electron have to travel an additional distance, and there will be an expansion in the band gap. And this band gap arises due to the interaction between metal s electron and oxygen, metal s orbit, and interaction between metal s orbit and oxygen p orbit, and this band gap arises. Okay. So, and we can move to the electrical property of transparent conductors. So as we said, the transparent conductors are highly conducting, but not like metal. Metals are having resistivity in the order of 10 to the power minus 7. However, the transparent conductors typically exhibit this resistivity that's shown in the table, this resistivity, this carrier concentration and mobilities. Okay. And so electrical property arises in transparent conducting oxide because of the free electrons in the conduction band and the oxygen deficiency. Two factors affect the electrical property. One is oxygen deficiency, and other one is the free electrons in the conduction band. Okay, so because of these two things, this host material is able to conduct electricity. Okay, so typically if we dope a semiconductor in a moderate amount, the carrier concentration will be in the range of 10 to the power 20 to 10 to the power 21 centimeter cube, and the mobility resistivity will be in the order of 10 to the power minus 4 ohm centimeter. And mobility will vary from 10 to 50 centimeters square per second. And this is the criteria or condition for what a material with a practical viability. A material with a practical viability. So this material can be used with these properties. The material can be a suitable transparent conductors for a practical application. So that are the electrical property. And we have two types of transparent conductors. There are N types transparent conductors and P types of transparent conductors. Fortunately, the N type transparent conductors shows very high conductivity, and on the other hand, the P type transparent conducting oxides are not so much conducting. It's still under development. So once we discovered a P type transparent conductor, a very efficient P-type transparent conductor, you may have a completely transparent device in your hand. Okay, so this is the development of transparent conductors with N-type conductivity and P-type conductivity. Okay. So transport mechanism, how these electrons are moving in a material surface, like how the electronic conduction, a transparent conducting oxide material. So we know that the material is having, say, it's a doped material. That means there will be a foreign impurity in the host crystal structure. So that means this foreign material should be able to contribute some electrons to the parent material. That means the doping should be aliovalent, not isovalent. The doping should be aliovalent. So the material can either contribute electron or holes to the conduction. Okay, so that will results in generation of large amount of carriers, free carriers, large amount of free carriers in the conduction band. So when this carrier concentration is large amount, these electrons can be moved by the application of potential difference across it. So see, for these free carriers have to be mobile. It should move in the crystal lattice like that. So if the carrier concentration is too much, that means beyond an optimum level, that will result in large resistance, because you can see that slide. That one is another thing. So if you have large concentration of carriers in the host crystal structure, what happens? The electrons cannot move freely. So the conductivity, the concentration of carrier should be in an optimal level. And main thing is that we need more electron with more mobility than larger number of carrier that are immobile. Okay, so moderate large concentration in the optimum level with high mobility is the criteria required for a transparent conductor material. Okay, and besides, see, so that means large concentration of carrier not only large concentration of carrier is not only the only requirement, but we need to have high mobility for that carrier also. Similarly, see, most of the transparent conducting oxides are in the form of thin films. So depositing a thin film will result in large number of grains and large number of grains on the surface. So that means there are possibility of scattering of electron at the grain boundaries. So that will also reduce the electronic conductivity. So fabricating a very high quality thin film is mandatory for high performance in TCs. Okay, so these are the factors that affect electronic conduction: the dopant, amount of dopant, and mobility, and the smoothness of the surface. Okay, so that are the requirement for a good TCU. And how can we develop it, a TCU? So you are showing a absorbance spectra of transparent conductor and band gap of it. So we need to develop a transparent conductor. We need material that is in TC space phase, and we are having that 5 material. So we need a host material first, then we need to select the dopants, and it should have a wide band gap. Then only it can transmit all the radiations falling on it. It should have very wide band gap. So it is a wide band gap semiconductor, the host material, and dopant appropriate dopant also should be chosen. So as we know, as we say, like the defect is good. So we all studying about the mainly the physics guys are studying about the defects in crystal, and we know that these defects are very good in order to develop new material. So these defects, crystal defects, can be utilized to develop new material. So in slide you are seeing indium oxide and tin oxide crystals. So see, and a pattern of lattice that is drawn by myself for my convenience. Okay, so you can see the bubbles, black and red. So this is how this is the black colored lattice is actually the host crystal structure. And when we dope some material into it, say tin oxide, this is black one is indium oxide, and if we are doping tin oxide into it, what happens? The tin oxide will occupy the position of indium. Tin will occupy the position of indium, and iron is 3 plus and Sn is 4 plus, so it can contribute 1 electron per atom. Okay, so this is called as the substitutional doping. The substitutional doping will provide an electron to sit in the position of another atom, and it can contribute some electron. Okay, so when we add the material into it, it can be resulted in the production of large concentration of free electron. So the crystal defect can be used to develop such materials. Okay, compared with the native, how we are selecting the dopants. Traditionally, there are some ideas about it, like the doping should be aliovalent. As we discussed, the doping should be aliovalent. That means the foreign material should be able to contribute 1 electron, or holes. So it is selected in such a way that the next row element in the periodic table is used as the dopants, like Sn4 plus for iron 3 plus and iron 3 plus for Cd2 plus. So this is a very good selection, like it can give high transparency and high conductivity. Okay, this is a very proven material, like indium doped cadmium oxide and tin doped indium oxide, etc. Okay, so and other ideas also work, criteria also work, like zinc oxide. Like I said previously, zinc oxide is a very versatile material that can be converted into p-type and n-type by changing the dopants into it. So zinc oxide zinc can be replaced by aluminum, gallium, indium, etc. And other group elements like silicon, germanium, titanium, etc. can also be used to modulate the properties of zinc oxide. Okay, and using these zinc oxide, tin oxide, cadmium oxide, gallium oxide, aluminum oxide, etc., a wide variety of binary, ternary, and multi-component TCs can also be developed. So these are the major criteria used for developing TCs, and there should be some rules for it, like how we need to choose the compounds. There should be a lattice match, first of all. If there are, if the lattice are very closely matching, what happens? The crystal structure of the parent material may be got undisturbed. That means without affecting the crystal structure of the material, we can introduce another material if there are so much of lattice matching, and the amount of dopants can also be higher in that case. And ionic size and radii, the dopant should have a comparable ionic size and radii with the parent material. And melting point. See, like I said previously, most of the TCs are in the form of thin films. So for thin film, to develop a thin film, we need a bulk material. So many cases, or most of the cases, the bulk material are fabricated from the raw undoped metal oxides and mixing together and heating it at a higher temperature. So if there are so much difference between the melting point, the one material cannot be diluted in the another material. So there should be a match between the melting point of the materials we are using. And we need to have an idea about the composition ratio. See, from the definition of doping, that It is the controlled addition of impurity into the host crystal structure. That means we cannot add the material whatever we want. We cannot do like that, because it will destroy the crystal structure. It will not give any output. So we need to add the amount in a precise manner, and we need to find out it, like solubility limit, doping limit, etc. Okay, so the composition ratio is very important. The amount should be in an optimum level. The dopant should be in an optimal level. Beyond that, the material does not work. Okay, and changing the structure, like novel structures, like nanostructures, etc., can be used to. You can use that idea also, changing the structure, and we need to have the elements that is abundant in nature, and we need to have the elements that is easy to deposit, fabricate, and it should be it should be green. It should be a green material, like that. So there are some criteria like this. These are ideal conditions. So we cannot always follow the ideal conditions. Like cadmium oxide is a very good TC material, but cadmium is a highly toxic material. So most of the time, the cadmium oxide thin films are not using as a transparent conductors. It is using as a transparent conductor in a concealed application or in a extraterrestrial applications, like that. So for solar cells, in a solar cell using in a concealed applications, the cadmium oxides materials are mainly using. It's a very good material, actually. And how can we fabricate a TCO? That is our question. Sorry. So as I said, no, TCOs are in the form of thin films. Almost all the devices, all the materials have, when it is used as a device purpose, it should be converted into a thin film format. Okay, so TCs also like that. TCs are also thin films, and we need to fabricate thin films. So we are having different techniques to fabricate thin film. So those who have idea about the material science and thin film technology, they must be knowing there are different conditions for that depositing thin film, like physical method and chemical method. So we will be discussing it later. So the thin film have to be deposited first of all. Then the properties of the material is have close dependence on the factors that we are using to deposit the thin film, like the oxygen partial pressure, the vacuum in the chamber, the distance between target and substrate, thickness of the film, etc. So we know that, see, if we deposit a thin film on a glass substrate for transparent conducting oxide application, what happens? If the thickness of the film is very high, the material should be highly conducting. If the thickness of the film is high, the material will be highly conducting. But if the thickness is very high, it should not be highly transmitting. Okay. Similarly, if we deposit a very thin film on a glass substrate, what happens? It is highly transparent but will not be highly conducting. So what we need a trade between transparency and conductivity. Like we need an optimum condition for high transparency and high electrical conductivity. So we need to identify in a trial and error method at what thickness the material is highly conducting and highly transmitting. So that is the major challenge coming to us while preparing, fabricating a TC. Okay, so that should be identified by trial and error method. And we have to find out that trade between transparency and conductivity. Then we have to find out the best material for that application. Okay. And besides, the fabrication techniques are very important, very important. See, if we deposit a thin film, for example, indium tin oxide, if we deposit an ITO by RF sputtering method, sputtering is a technique used to deposit thin film, sputtering method, the same material we fabricated by using another technique shows different properties. Okay, so the deposition parameters, the deposition techniques, etc., will have close influence on the property of TCs. Okay, even though it is same material, it show different property, different conductivity, different transparency, like that. Okay, so we have to be careful in identifying the material, identifying the thickness, identifying the transmittance, and identifying the best method of deposition, etc. during the fabrication of a TCO. Okay, so please excuse me if you are already know about these things. Like these are common things. Like what are the methods to deposit transparent conducting oxide? It's a common thin film deposition techniques. We are having different techniques to deposit fabricate TCs. We can use physical methods and chemical methods. We can use sputtering method. We can use the chemical method like spin coating, dip coating, etc. Okay, and among this, the sputtering is the most important technique. Most of the highly efficient TCs are made by using the sputtering technique. Okay, so all these techniques can be used to deposit a transparent conductor. These are some slides that showing the fabrication of TCs by vacuum evaporation method. Vacuum evaporation method is a simple 3-step process as shown in this slide. Like we are having a target material, it should be evaporated into gas phase, and it should be coated onto a condensated onto a substrate kept at high temperature. So this is the 3 phases in 3 steps in the deposition of a thin film. Like a solid bulk material have to be evaporated by means by any means, like heating it by a resistive method, by a beam of electron, by a beam of laser pulses, or etc. And it should be go into the gas phase and deposited on the substrate, like that. So the steps are very simple, but the process is not simple. Getting a very high quality thin film is a task. Very high quality thin film is still a task. So this is the simple 3-step, but not so easy. By means of its surface smoothness and by means of its crystal structure, it is a tough job. Okay, so this technique can be used to deposit a TC. Sputtering is the most important technique to deposit a TC because it gives it can be used. The sputtering can be used to transfer all the exact chemical composition onto a substrate. So that is the advantage of sputtering. So instead of evaporating, what happens is that there will be a chamber. Inside the chamber, there will be a target, and there will be a substrate, and there will be a inert gas inside the chamber. And applying a large potential across this inert gas, this gas will be ionized and turn into plasma. And this highly energetic plasma will hit on the target material, that will release the target atom, and that will be eventually deposited on a substrate. Okay, so this is simply the sputtering process. So this method is one of the best proven method in producing these TCs. Okay, and another method, this is also like sputtering. This technique is also very important. We have used this technique to deposit our thin films. So in this method, the stoichiometric transfer of the bulk material into the substrate is possible because it completely take the exact chemical composition of the target into a substrate. So PLD, pulsar laser deposition, is also a very highly effective method in depositing a transparent conductor. Okay. So before that, in order to make this material, we need to have a target material. Okay, so in the case of a physical vapor deposition technique, we need a target material. Okay, so how the target material can be prepared? Many methods are there. What we are doing is we use solid state reaction. Solid state reaction is a technique that is producing a material by mixing it together and heating it at high temperature. Solid state reaction. So we will mix zinc oxide and tin oxide together, mix it well, heat up to high temperature like 1200 or 1300, like that. And the steps will be repeated in many times, until we get a solid solution. What is a solid solution? A solid solution is like this: a dopant material is completely dissolved in a parent material. That is called as a substitutional solid solution. So substitutional solid solution means all the foreign material will be dispersed, diluted into the host structure by using the heat treatment and the rigorous grinding of it. Okay, so we will get a substitution solid solution by this method, and we can have the other things like the alloys and compounds also, but the ratio of the compounds will be different here. So in that case, for example, say in order to deposit aluminium doped zinc oxide, okay, I will select tin doped zinc oxide. In order to synthesize tin doped zinc oxide, what we do? We will the ratio 2% of zinc oxide and 98% of 2% of tin oxide and 98% of zinc oxide. Mix it together, heat it, then again mix it, grind it, then heat it, and finally we have that substitution solid solution. But in the case of a alloy or a compound, the percentage will be almost equal, like 50% zinc oxide and 50% tin oxide. It will be a new compound with a new structure. Okay, so that also be synthesized by this method, but we have to be aware about the composition. Okay, so this is how we prepare the target material for thin film. This target material can be used in this method, these techniques employed into this technique, and finally we will get a TC material. These are the process that happen in a solid state reaction. So this is I'm talking about the vacuum deposition technique in order to synthesize a TC. And however, on the other hand, say these vacuum deposition techniques are like a tedious job. We need high vacuum, we need a lot of instruments, we need a lot of equipment arrangements. Like for an electron beam, we need a very highly energetic beam of electron, and for pulsar laser deposition, we need a very high quality laser source and experimental arrangements like that. So this is a tedious job, depositing a TC in a thin film by using a vapor deposition technique. On the other hand, the chemical methods are simple, very simple method, very simple technique. We need to prepare a solution of it, spray the solution on a substrate. Substrate is commonly glass quartz. The substrate will be kept at high temperature, and when this sprayed material, this sprayed solution falls on the surface, it will become oxidized and condensate on the substrate and forming a thin film. Okay, this is what happens in the spray pyrolysis technique. There are other techniques like spin coating and dip coating, etc. are there. This is one of the example I'm showing. So the solution may be indium chloride, tin chloride, zinc acetate, etc. And the oxygen will be taken from the environment. So we can deposit TCs by spraying the solution onto the substrate. Okay, very simple technique. But one thing you have to be careful that the thin film deposited by this method will not have the quality that the physical PVDs are having. I mean, physical deposition techniques are having. So these thin films are easy to deposit, less expensive, but less quality. But PVDs are very high quality, very good thin films, but more expensive. And this is an example. Other methods are there, like spin coating, dip coating, etc. are there. So what we do after depositing a TCO material? So we have to study the material. We have to study the material by means of different technique. Like we have to understand the structure of the material. We have to understand the surface of the material, surface features of the material. And we, of course, the most important part is the optical and electrical properties. It should be highly transparent and highly conductive. So these things have to be measured after depositing a transparent conductor. Okay, why we need to do all these things? Because the property, the electron mobility, electron conduction, and optical properties are very closely related to the structure of the material. And The electrical property, of course, is very closely related to the surface, the smoothness of the surface and the chemical composition on the substrate. Okay, so the surface, chemical composition of the surface. So, so these things have to be analyzed by different advanced and conventional technique in order to study the efficiency of TCs. And electrical properties can also be measured. Yes, any question? Okay, somebody raise the hand. Okay, electrical property can be measured by means of a simple for-probe method that may be available in any PG lab of MSc Physics department, but we need much more advanced device. Okay, like the probe should be very sensitive like that. So we need a for-probe technique, and another method is a Hall measurement van der Pol method. See, you can see the Hall measurement van der Pol method can be used to study any surface. See, thin films will not have uniform size and shape, so any size surface can be studied by means of a van der Hall measurement method. Okay, so this method can be used to measure the electrical property, and optical property use a UV visible spectrophotometer to understand the percentage of transmissions, the absorption on set band gap, etc., energy band gap, etc. Can be found out from a UV visible spectrometer. And what are the from the basic science or physics point of view, what is more important? More important is describing the structure property relationship and surface property relationship. So we need to concentrate, we need to explain the physical properties of it by means of its structure and surface. So that is more important for us, and we need to concentrate on that one also. So I can say some examples. So you can see that ITO is deposited. ITO film is deposited. So you can see the X-ray diffraction pattern from the crystal structure. It is identified that it is ITO only, and it shows the resistivity in the order of 10 to the power -4 ohm centimeter. This was work conducted in 2009 by Kono et al. So you can see the highly conducting indium tin oxide films are deposited by that method. And I will also explain, say, the resistivity, Hall mobility, etc. So these things are discussed, discovered by using different techniques. Okay. Similarly, zinc oxide, you can see a zinc oxide thin film, which was, I think it was reported by Material Research Center of Indian Institute of Science. They have also deposited. See, you can see the variation of indium concentration in zinc oxide, but its crystal structure is unaffected. So that means even though we increase the number of amount of cations inside the foreign crystal matrix, it should not result in the it should not affect the crystal structure drastically. That should be the point. We have to be careful when we are fabricating a bulk material or a thin film material. The phase purity should be maintained. And we are having another class of material called as multi-component oxide material. So what is the advantage of multi-component oxide material? See, I precisely work on this field, multi-component oxide material. That means there will be different number of cations and different amount of cations will be there. And by changing the number of cations and by changing the number of cation and amount of cation, the electrical, optical, and chemical physical properties can be modulated in a required manner, in a precise manner. Like if you want a material with 3.4 electron volt, particularly, we are having a material with 3.2 electron volt. So we need to find out at what percentage the material is going to be a band gap of having 3.4 electron volt, like that. So the tuning of the material is possible by forming new chemical composition with the existing compounds. So that is multi-cation or multi-component oxide materials. So these are special class of materials. Like it uses the stoichiometry of the compound, that is, I said, defect in the crystals. Like we called it zinc oxide, but actually it is not zinc oxide. There will be some defect in zinc oxide that will help us to tune the material or help us, give us a possibility to import something into the zinc oxide like this. So stoichiometry and non-stoichiometry should be identified for all the compound in order to make such a composition. Okay. So these are some works we are reported on the multi-component oxide material. A few works which was reported in these materials. Like see, this is a bulk material, target material that I prepared. Say it contains different cations, like it contains zinc oxide, zinc, tin, gallium, etc., etc. But even though, see, you can see the cations, the number of cations are changing, but the crystal structure is unaffected. Sure. The crystal structure is unaffected. So that means even though we are changing the composition of the material, the crystal structure should be unaffected, and that will make a substitutional compound, and the substituting element can donate some electrons to the compound. So this is the X-ray diffraction pattern of the bulk material. Okay. And this bulk material can be utilized to deposit a thin film like this. Okay, so this is the thin film you deposited from that bulk material and formed a thin film by pulsar laser deposition technique. So you can see that the material is having same crystal structure with prominent peaks are here and some peaks are absent because the thin film are not dense crystalline like a bulk material. So we will miss some elements, some peaks, but it is having the same crystal structure to that of a bulk material. And to study the structure, we can also use the Raman spectroscopy, and the lattice dynamics can be studied by using the spectroscopy. And the thin film, this is the X-ray diffraction pattern that we use to study the crystal structure of that TC material. And this is the surface. The surface is very important. The smoothness of the surface is very important, because if the surface is not smooth, the electron will scatter from the grain boundaries. And if electrons scatter from the grain boundaries, that will result in high resistivity. So the smoothness of the surface is very important in the case of any thin film, and especially for TCs. Okay, and specific properties like surface analysis is very important. Surface analysis comes two categories, like it should have very smooth surface. It should tell us about the smoothness of the surface as well as the chemical composition. So one of the best methods used to analyze the chemical composition of the surface is by recording a X-ray photon spectra. So X-ray photon spectra will give the elements present in the sample. You can see the slides in the right hand side, the elements present in the sample, as well as the oxidation state of the element, as well as the percentage of elements in the compound system. So this is one of the best tool to analyze the chemical composition of the compounds. And see the beautiful optical transmittance spectra that I obtained for that thin films. See, this is showing a transmittance up to 80 above, like that. So by changing the compositions, the transmittance and band gap, etc., can be varied here. Okay, so see this interference pattern observed in the transmittance spectra are due to the very high smoothness of the surface, high quality of the surface, showing high quality of the surface because the path difference throughout the sample is same for the electromagnetic radiation, and it gives an interference pattern. Okay, so we have got highly transparent films, and we need to check the conductivity also for that. And we check the conductivity, band gap also determined from the UV visible spectra, and we tune the band gap by changing the cations like this. Okay, and electrical properties. What we have done is a multi-component oxide material, so we cannot expect a conductivity that is similar to that of indium oxide. So we have got conductivity in the order of ohm centimeter, like this ohm centimeter. So this cannot be used as a optical, like a TC coating for a mobile phone or something like that, but it can be used at a buffer layer or low conductivity applications. Okay, but still it is conducting with low resistivity. So we have got this. And mobility also, we have got a substantial amount of free carriers on the surface, and the mobility also very good. We have got very high mobility and very high concentration. So these things we have analyzed by obtained by from those studies. And see, this is another work that we have done. The thin films deposited, the TCs deposited by spray pyrolysis method. See, you can see the optical spectra. The optical spectra will tell us about the quality of the thin film. See, you see these transmission spectra and this transmission spectra. So this is very high quality, indicative of very high quality of thin film. And this transmission spectra indicative of a very low quality surface feature of a thin film, because there are no interference pattern. That means the thickness of the TC on the glass or quartz substrate is not uniform. But we have got good resistivity and good electrical conductivity here. Okay. Since it is zinc oxide and it is doped with a single material, it can show good conductivity. So that is what I have to discuss here. And these are some future applications of TCs. Like this is Toyota Dream House, that all the electricity requirement of this house should be met from the photovoltaic system that is fabricated on the windows and glass doors, and completely transparent mobile phone or mobile accessory or something like that. And thermochromic and electronic chromic windows like that. By using that, you can naturally control the temperature inside a room or something like that. Okay. So these are some future application of TCs. Not future, it's already discovered, but need to be improved. Like completely transparent devices are not discovered till date. I think, I don't know. Maybe Dr. Aneesh can answer this. And these are some common applications of TCs that we have already discussed. And what are the scope? From the point of view of a condensed matter physics, we need to study a lot of about the material properties, like structure to property relationship and surface to property relationship. The photoluminescence spectra of this material will provide deep information about the electron transitions. And we need to study the oxygen deficiency, how it affects the properties of the material. So we can use vacuum annealing in order to make the thin films further oxygen deficient. That will increase the conductivity again. And a theoretical calculation, band prediction calculation, etc. are the possibilities still on it. And we need P-type material. P-type TCOs are very important. So we need to find out new P-type material. So one of the hot areas of research is discovery of P-type material, and reduce the cost of TCs and easy deposition, etc., etc. Should be the future scope of this thing. So I think I can conclude. Thank you. If there are any questions, I can answer.
Thank you, sir. Thank you, Professor Jayaram, for the wonderful session. I hope the participants have gained enough knowledge on the TCOs, thin film solar cells, and the basics of this thin film solar cells. So the participants, if you want to post the questions, you can post the questions to Professor Jayaram. Participants, please post your queries, your research queries, if any, to Professor Jayaram, please. Yes, participants could please post their questions because it's a wonderful opportunity. You could ask him about the research opportunities or whatever you are trying to explore in the field of thin film solar cells. So participants can please utilize this opportunity to ask Professor Jayaram regarding this thin film solar cells and TCOs. Okay. Okay, so thank you, Professor Jayaram, sir. It was a wonderful session. It was a rigorous session on the basics of the strong fundamentals of the thin film solar cells. And I hope the participants have gained enough knowledge on the basis of these thin film solar cells. I hope some of the participants will turn to Professor Jayaram for their research opportunities. So thank you, sir. Thank you so much for addressing the FDP. We will be closely associating in further FDPs in future. Thank you. Thank you so much, sir.
And,
Thank you very much. Thank you, Dr.
And
Aneesh.
once
Thank
again,
you, John.
and we have Dr. Deepthi, Associate Professor from Presidency University, Bangalore, to propose vote of thanks.
Thank you, Dr. Sunish. A good teacher can inspire hope, ignite the imagination, and instill a love of learning. Good afternoon to one and all present here. I am Dr. Deepthi, Associate Professor in Department of Physics, Presidency University, Bangalore. It is such an honor for me to get this opportunity to propose the vote of thanks on behalf of the participants. At first, I would like to thank Dr. P. Jayaram, Assistant Professor, MES Ponnani, Kerala, for delivering an interesting and inspiring lecture on transparent electronics, techniques and applications. Sir, you have explained very well how a material can be simultaneously transparent and conducting, features of transparent conducting materials, etc. I am sure that the participant must have gained knowledge by attending this lecture. Thank you, sir. I must thank the organizing team, MES College of Engineering, the ATAL team, for organizing this FDP in a successful manner. I thank all the participants for their active participation. Other than their participation, this FDP won't be a successful event. Thank you all. Once again, I thank all the team members, the speaker, and the participants from the participants' point of view. Thank you all.
Thank you, Dr. Deepthi. Thank you, Jayaram. Yes. Thank you.
Thank you.
Thank you, sir.
So we have the minutes. Yeah, you can leave now, sir. Dr. Jayaram, you can leave now.
Thank you. Thank you very much.
Thank you. So dear participants, attendance and the feedback link is provided in the chat box. Requested to fill attendance link and feedback link.